You're listening to DTFHN for April 5th, 2026. I'm your freely distributable host, Jack Haxman. We are your daily tech feed for Hacker News, a website where strangers yell about software until something useful happens. Today, the blueprints are on the table and nobody's charging admission. Let's go build something. One of the top comments on this thread links to a paper from March 2026. Brevity Constraints Reverse Performance Hierarchies in Language Models. The finding is striking. When you force an LLM to be concise, the quality of its reasoning can actually degrade. The model isn't just trimming filler. It's losing the internal scaffolding it uses to think. And that tension is exactly what makes this project worth talking about. Caveman is a Claude Code skill. One line to install. That rewrites how the model talks to you. Articles gone. Pleasantries gone. I'd be happy to help you with that. Extinct. The before and after examples are genuinely compelling. A 69-token explanation of React Ru renders becomes 19 tokens. Same diagnosis, same fix. 75% less output. Think of it like pruning a fruit tree. A master gardener knows which branches are structural and which are just foliage. Cut the right ones and the tree produces more fruit with less energy. Cut the wrong ones and you kill the limb that was about to bear. The commenters on Hacker News are split on exactly this question. One person reports that caveman speak Claude actually answers worse. More misunderstandings, more back and forth to clarify, ultimately more tokens spent in total. Another points out the real bottleneck isn't output tokens at all, it's input. The agent is ingesting directory trees, code files, tool outputs, entire code bases. Shaving words off the response is optimizing the wrong end of the pipe. Both of these critiques are valid, and neither of them diminishes what matters here. What matters is that someone saw a viral observation about language model efficiency, built a tool in the open, published it under MIT, and made it a one-line install. The entire thing is a Claude Code skill. A text file that reshapes behavior. No model fine-tuning, no proprietary wrapper, no API middleman extracting a fee, just a prompt engineering pattern shared freely that anyone can fork, modify, or learn from. This is how the ecosystem is supposed to evolve, not through closed optimization passes sold back to you as a premium tier, but through a GitHub repo that says, "Here, this works. Take it, make it better." The deeper question the paper raises is real. There may be a fundamental trade-off between brevity and reasoning quality in transformer architectures. The tokens we dismiss as filler might be load-bearing cognitive scaffolding. That's a serious research problem worth serious investigation. But the way you investigate it is by building tools like this, measuring the results, publishing the findings, and letting 1,000 engineers iterate. The pruning shears are on the table. The tree is right there. Start cutting and see what grows. We talked about trimming what's unnecessary. Pause. Now let's talk about building something new from scratch. Story 2, Lisette. The help hint on that match exhaustiveness error reads, and I quote, "Handled the missing case severity, critical E.G. Severity, critical low, severity, critical error, code, a complete copy-pastable fix. Inline at the point of failure." That detail tells you everything about what Lisette actually is. In 1995, when Java launched, one of its quietest selling points was that it compiled to bytecode. Write once, run anywhere. The language wasn't revolutionary. The compilation target was. Java piggybacked on the JVM's portability to get adoption, then used that adoption to enforce its own type discipline on code bases that would otherwise have been written in C with all the footguns loaded. Lisette is running the same play 21 years later against Go. The compilation target is Go source code. Your Lisette compiles down to readable, importable Go, which means every Go library, every Go deployment pipeline, every Go team's muscle memory. It's all still there. You don't migrate, you layer. And the layer adds exhaustive pattern matching, option types instead of nil, immutable by default bindings, result types that refuse to be silently ignored. The Rust safety model delivered through Go's ecosystem. Look at the nil error. A developer writes return nil, and the compiler doesn't just reject it. It explains that absence is encoded with option T in Lisette, then suggests none. The compiler is teaching the language while enforcing it. Every error message is a micro-tutorial. That's a design philosophy borrowed from Elm and refined by Rust's compiler team over years of iteration, now applied to the Go surface area where nil pointer panics are. Conservatively, the single most common production failure mode. The Hacker News comments circle around an interesting question. Why not just use Rust syntax exactly where the features overlap? Why import foo.bar instead of use foo::bar? The answer is in the compilation target. Lisette isn't pretending to be Rust. It's a bridge language. The import syntax mirrors Go's because the compiled output is Go. And developers reading that output need to trace the mapping. Form follows, function follows target. One commenter asks about compiling to Go assembly instead of Go source. That would be a different project entirely. A project that severs the readability link between input and output. Lisette's value is precisely that the output remains legible. Go, you can audit it. You can debug it in Go's toolchain. The abstraction is transparent by design. This is a single developer project. Open source building type safety is a layer rather than a replacement. The tools exist. The Go ecosystem is right there. Someone just handed it a better type checker. From building better abstractions for code to building the actual silicon that runs it. Pause. Someone made a game where you design a GPU from scratch. Let me work with the information available from the HN post and comments. NVIDIA. Even the name is doing work. A wink at the green giant while you're literally wiring transistors by hand. Let me make the case against this. Educational games about hardware are a graveyard. NHE Tetris exists. Turing Complete exists. Multiple commenters point this out. The argument writes itself. We don't need another logic gate simulator. The space is covered. Go read a textbook, play an existing game, move on. Except here's the thing about that argument. It assumes learning resources are fungible, that a textbook and a game and a interactive tutorial all scratch the same itch. They don't. One commenter is a veteran of deep sub-micron full custom mixed signal integrated circuit design. More than a decade of experience, and can't pass the first level. Another commenter lacks the basic knowledge to parse the tutorial. These are opposite failure modes in the same product, and that's actually the tell that something interesting is happening. The game is finding the gap between I've designed real silicon and I've never seen a transistor diagram, and it's trying to bridge it. That gap is where GPU architecture education actually lives. In the messy middle where theory meets physical intuition, the creator's motivation is disarmingly honest. Thought the resources for GPU Arch were lacking. That's it. That's the whole pitch. Someone looked at the educational landscape for one of the most consequential pieces of computing hardware on the planet. The thing currently reshaping every industry, the thing nation-states are sanctioning each other over. And said, the learning materials aren't good enough. I'll build something. Now, apply the architecture test. This is a browser game. It's on someone's personal domain. The knowledge of how GPS works. From most transistors to latches to, presumably parallel compute units, is being made interactive and free. Compare that to the actual GPU industry, where architectures are locked behind NDAs, where CUDA is the moat, where the hardware-software stack is deliberately opaque to maintain vendor lock-in. Someone building a game that teaches you how the black box works is a small act of liberation. The comments reveal the real design challenge. Users want a hint system. A show me the answer after 10 attempts button. That's not a complaint. That's a feature request from people who are engaged enough to fail 10 times before asking. The latch level where someone solves it with a single OR gate and isn't sure if it works in practice. That's the exact moment education happens. The doubt is the lesson. One person builds a GPU in a walled garden and charges for access to the knowledge. Another person builds a game that hands you the wiring diagram and says figure it out. Builder culture at its most literal. Here are transistors. Here is what a GPU needs to do. Now wire it yourself. The tools exist. Someone just made them playable. We talked about open tools building trust. Now let's see what happens when governments hand that trust to two corporations instead. In U19, the European Commission fined Microsoft €240 million for bundling Internet Explorer with Windows. The argument was straightforward. A government cannot allow a single vendor to become the mandatory gateway to a public resource. It took a decade of litigation, but the principle held. You do not build public infrastructure on private toll booths. 27 years later, Germany is building its digital identity system. The implementation of the European Union's eIDAS regulation. And it requires device attestation from Apple or Google to function. Your government-issued credential, the thing that proves you are you to your own state, will not work unless a company in Cupertino or Mountain View vouches for your phone first. Follow the logic all the way down. The technical justification is something called Mobile Device Vulnerability Management. The wallet needs to verify that your device's hardware key store hasn't been compromised, that the operating system is current, that no known vulnerabilities exist that could let an attacker with high attack potential extract your keys. Reasonable enough on paper, but the only way to get that verification on commodity mobile hardware is through Platform Attestation, APIT. Google's Play Integrity, Apple's Device Check. These are proprietary services, controlled entirely by their respective corporations, with terms of service that can change on any Tuesday. A German implementer in the comments confirms it. They had to use attestation mechanisms per the eIDAS implementing acts. That doesn't work without operating system support. And operating system support means two companies, both American, both answerable to American courts and American foreign policy. Someone raises the case of a sanctioned judge from the International Criminal Court who lost access to their Google account. Imagine that judge trying to authenticate with a European government. Their identity doesn't stop being valid because Google's compliance department got a letter. The eIDAS specification itself doesn't require specific hardware. It stores verifiable credentials and cryptographically signed attestations. The dependency is a design choice, not a technical inevitability. Germany chose to outsource the root of trust for its national identity system to two foreign corporations because building an open attestation framework was harder. The commission that once fined Microsoft for bundling a web browser is now presiding over an identity system that bundles citizenship with the terms of service agreement. The possession factor. the thing that proves you hold the device, is secured by a key store you don't control, on an operating system you can't audit, verified by a service you can't replace. Europe spent 20 years fighting for digital sovereignty, and then handed the front door key to the same two landlords it was trying to regulate. The alternative exists: open hardware attestation, reproducible builds, community-audited firmware. It is harder, it is slower. It is also the only version where your identity actually belongs to you. We talked about tools that respect you. Sup-a-can tray. Here's one for creators. OpenScreen just dropped as an open-source alternative to Screen Studio. Pixie.js. They built the rendering pipeline on Pixie.js. That means every zoom, every pan, every motion blur transition is running through WebGL, hardware accelerated in real time. Inside an Electron app. No shelling out to FFmpeg for preview frames. No waiting. You drag a zoom point, you see it render. That is genuinely clever engineering for a project whose README says, quote, "I'm new to open source. I don't know what I'm doing." OpenScreen is a free, open-source screen recorder that does the one thing people actually pay Screen Studio $29 a month for: making product demos look beautiful. Automatic and manual zooms with customizable depth. Motion blur on pan effects. Annotations, trimming, speed ramping, custom backgrounds. The full workflow from capture to polished export, built in React and TypeScript. MIT licensed, no gotchas. The question nobody in that comment thread is asking: why did beautiful screen recording become a subscription in the first place? Screen capture is a solved problem. Your operating system already does it. What Screen Studio actually sells is the post-processing. The smooth zooms, the drop shadows, the make my terminal demo look like an Apple Keynote pipeline. And that pipeline is math. It's interpolation curves and compositing passes and resolution scaling. None of it is secret. None of it requires proprietary technology. It requires someone to sit down and build it. One developer did. The zoom is preset based right now, and people in the comments are already asking for a slider. Someone else posted a demo they made with it, and it looked genuinely good. Another commenter pointed to Cap, a different, open-source screen recorder, and that's the thing worth celebrating. This space now has multiple free options competing on quality, not on the lock-in. The README is almost apologetically modest. It calls itself sort of an alternative. Says it's much simpler. Tells you to go buy Screen Studio if you need the fancy stuff. But the architecture choice tells a different story. You don't build a WebGL rendering pipeline if you're planning to stay simple. You build it because you know where this is going. The tool exists, the code is open, ship your demo. 6 stories, and we haven't even touched the weird stuff yet. Story 6. Introduction to Computer Music. Let me work with what's available from the comments and title to write this segment. What do computers dream about when they listen to music? It's not a frivolous question. It gets at something fundamental about the relationship between computation and creativity, between signal processing and soul. And this textbook from 2009, freely available as a PDF, is one of the clearest maps anyone has drawn of that territory. Nick Collins wrote Introduction to Computer Music as a bridge. One commenter who used it as a student describes it as DSP-focused with musical applications. More approachable than the legendary Curtis Rhodes tome from MIT Press, which remains the field's intimidating Bible at over 1,000 pages. Collins gave us something different, accessible enough to learn from, rigorous enough to build on. Run this forward. Imagine you're a musician in 2009 reading this for the first time. Fourier transforms aren't abstract math anymore. They're the reason your reverb plugin sounds like a cathedral. Additive synthesis isn't theory. It's the architecture behind the pad sound you've been chasing for months. The math was always there inside the music. Someone just handed you the lens to see it. One of the comments on the Hacker News thread links to something extraordinary. Juan Garcia Castiello published a book on electric music in 1944. 1944, the lineage of computational thinking about sound goes back further than most people realize, and every generation rediscovers it with new tools. Collins was writing in the Super Collider era. Today, someone picks up this same knowledge and applies it in a browser with the Web Audio API. The fundamentals don't expire. There's a footnote in the book, apparently, where Collins apologizes to future readers for speculations about AI that might age poorly. The fact that he was thinking about that in 2009 tells you something about the quality of mind at work. And the Hacker News commenters note that attitudes toward AI in music have shifted dramatically since then. What felt speculative is now a production tool. The commenter who started with Ableton Live and fell in love with the cottage industry of plugins and instruments. That's the downstream effect of knowledge like this being open. Every synthesizer plugin, every granular sampler, every spectral processor traces back to the DSP fundamentals that Collins laid out. The ecosystem exists because the knowledge was shared, not hoarded. The PDF is free. The math is timeless. The instruments you build with it are yours. Moving on. I've spent years building systems where the hardest bugs aren't the ones that crash. They're the ones where you can't even observe the failure state. You know something's happening because the outputs exist, but the process itself is invisible. That's what the European eel did to science for 2,000 years. Aristotle wrote about eels. He thought they spontaneously generated from mud. And for most of recorded history, that was about as good as anyone's explanation, because nobody had ever seen an eel reproduce. Ever. Anguilla anguilla. A creature that lives in European rivers for decades, sometimes 50 years, and then one autumn vanishes. If you cut one open during its freshwater life, you find no reproductive organs. None. They don't exist yet. The eel is waiting. And what it's waiting for is a 5,000-kilometer swim back to the Sargasso Sea, a patch of the North Atlantic surrounded by currents but touching no shore, where it will develop sexual organs for the first and only time, spawn and die. Its stomach dissolves before its gonads form. The entire animal is optimized for one final act that destroys it. And Yedine to say, a Danish biologist named Johannes Schmidt found eel larvae in the Sargasso Sea and hypothesized this was the breeding ground. It took 100 years to confirm he was right. Kim Arstrup and his team at the Technical University of Denmark finally tracked adult eels from European waters all the way to the Sargasso, the first direct confirmation of what Schmidt suspected. A century between hypothesis and observation. That's how difficult this organism made itself to study. And the stakes are real. European eel populations have collapsed more than 95% since the 1980s. Dams block their migration route. Habitat loss, pollution, overfishing. The usual litany of human infrastructure making the world inhospitable to a species that was already running one of nature's most precarious reproductive strategies. This research matters because you cannot protect What you do not understand, the data is published. The tracking methodology is open. Other researchers can build on it. That's the only way conservation science works. When the knowledge compounds freely, when every marine biologist on the planet can access the same findings and apply them to local policy. The eels kept their secret for millennia. Now that we finally have it, the question is whether we act on it fast enough to matter. We talked earlier about knowledge wanting to be free. Pause. LLM Wiki is what that looks like when someone actually builds the infrastructure for it. Every database query has a cost. In RAG, that cost is paid on every single question. The system retrieves chunks, assembles fragments, synthesizes an answer, and then throws all of that work away. Next question, same process. The computational pattern is identical to an interpreter running the same program over and over without ever compiling it. Andrei Karpathy published what he calls an idea file, a prompt you paste into your LLM agent that instructs it to build a persistent wiki instead of doing retrieval. When you feed it a new source, it doesn't just index the document. It reads it, extracts entities, updates existing pages, flags contradictions with prior sources, and weaves the new information into an interlinked markdown structure. Obsidian on one side, the LLM on the other. The wiki is the code base. The LLM is the programmer. You're the architect. The obvious objection, and the comments surface it immediately, is that this is just RAG with extra steps. You've built an index, the LLM still has to read the wiki pages to answer your question. Fair. But consider what's actually changed. In a RAG system, synthesis happens at query time every time. In the wiki pattern, synthesis happens at ingest time once. The cross-references exist before you ask. The contradictions between your sources have already been identified and documented. You're querying a compiled knowledge structure, not raw fragments. A subtle objection, model collapse. LLM-generated text feeding back into LLM-maintained documents, compounding errors and smoothing away nuance with each pass. This is a real failure mode, but the architecture actually mitigates it. The raw sources persist alongside the wiki. The wiki is a layer, not a replacement. You can always diff against the original. What makes this worth paying attention to is the design pattern itself. The idea file is 40 lines. It's not a product. It's not a startup. It's a prompt you copy and paste. The entire system runs on tools that already exist. Markdown files, a text editor, an LLM agent. The knowledge compounds because the structure compounds. Every source you add makes every future query cheaper. That's not RAG. That's a personal knowledge compiler, and the blueprints are free. Now let's go from software all the way down to silicon, because open source doesn't stop at code. Story 9. Aegis. 2 comments. The whole Hacker News thread for an open source FPGA built from the silicon up, and it gets 2 comments. One says neat project and immediately pivots to other teams doing similar work. The other just wants to buy one. Meanwhile, every thread about some VC-backed wrapper around a closed API gets 300 replies arguing about pricing tiers. Let's break down what actually happened here. For decades, the FPGA world has had a specific bottleneck, and it's not the tooling. YOSIS exists. NextPGAR exists. People have reverse-engineered lattice and Gowan bitstream formats through sheer stubbornness. The missing piece was always the fabric itself. The actual silicon design that everything else targets. That part stayed locked behind Xilinx, Intel, latest. You could write open tools that talk to proprietary chips, but you couldn't build the chip. Aegis generates the entire FPGA architecture in ROHD. That's a Dart-based hardware description framework. An output synthesizable system of bug, LUTs, block RAM, DSP tiles, SIRs, clock management, the full stack, and the tape-out pipeline runs through OpenRoad to produce GDS2 files you can actually send to a foundry via wafer.space. 2,800 LUTs on the first device. That's tiny by commercial standards. A Xilinx Arctic 7 has over 200,000. But the Arctic 7 is a product. Aegis is a seed. The parameterization means scaling up is changing numbers in a config, not redesigning architecture. The real first principles question with FPGAs has always been, why is reconfigurable computing the most democratizing form of silicon, controlled by 3 companies? The answer is that fabrication was expensive and closed. Foreman PDKs and shuttle services changed the economics. Aegis is what happens when someone actually follows that thread to its conclusion. The whole thing builds with a single NIX command, working silicon, open blueprints, 0 gatekeepers. Open blueprints for silicon pause. What about open blueprints for how a programming language actually works? Let's talk Ruby. Page 47 of the README. That's where the array splat desuggering lives. A Ruby function that does exactly what the asterisk does, written out longhand, because nobody had ever bothered to document the full semantics in one place. This is a cartography project disguised as a programming language experiment. Ruby's syntax is like a cathedral that's been renovated 17 times. Every wing makes sense if you know which architect added it and why. But the floor plan as a whole? Nobody has the complete map. The official documentation describes rooms by pointing at other rooms. The array literal page mentions splat behavior in passing, under implicit array assignment, which is like explaining how a carburetor works in the chapter on seat belts. What Squadet is doing with RubySyn is translating Ruby into Lisp notation. Not because Lisp is better, but because Lisp is boring. Parentheses are the X-ray machine of programming languages. You cannot hide implicit behavior inside parentheses. Every operation becomes visible. Every piece of sugar dissolved. The beautiful comedy here is that Ruby, a language beloved for its elegance, turns out to have corners that even experienced Rubyists navigate by muscle memory rather than understanding. Nil.to returns an empty array. Splat on a hash gives you pairs. These are obscure edge cases. They're behaviors people rely on daily without being able to point to where they're specified. And the whole thing is on GitHub. Fork it. Argue with it. Add the corners you've discovered in your own decade of Ruby. This is how language knowledge should work. Not locked in one person's head or buried in a mailing list archived from 2004, but laid out where anyone can read it, challenge it, improve it. The spec directory alone is worth the visit. Corner cases as unit tests. That's documentation that can't lie. This has been your daily tech feed for Hacker News for April 5th, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voice by Quen 3 TTS. Not affiliated with Hacker News or Y Combinator. Now go share something you know with someone who needs it. We'll see you back here tomorrow.